Good morning. In study lectures, what we talked? We talked how the forces working on the structure as well as the movement caused by the structures will be borne by the footing. And finally, the footing transmits this moment and forces to the soil which is available below the base of the footing. We also talked about the shallow foundation and deep foundation. In case of shallow foundation, the moment and the forces acting on the footing is taken care of by the shear resistance or shear strength of the soil available below the base of the footing, right? Whereas in case of deep foundation, or we can take the example of pile foundation. In case of pile foundation, how the forces of the structures, moment working on the structures will be taken care of by the pile foundations. We have also talked in the fifth semesters that the friction forces working along the periphery of the pile as well as the end bearing. That means the end bearing means what? The the load will also be taken care of at the bottom of the pile. So these two are going to take care of the forces and moment caused by the structure on the footing. Here footing caused by the footing means here we are going to take as a pile foundation, which is deep foundation. In addition to that, we also talked yesterday what are the various types of load which we have to consider in the design of foundation: dead load, live load, water pressure, earth pressure, snow load, seismic loads, right? So all things we talked yesterday. We also talked about the design of the ST footing. ST footing means continuous footing. In case of continuous footing, how we can calculate the area of the footing? See, in case of the ST footing, we consider two things: how we can calculate the size of the footing, how we can calculate the depth or thickness of the footing. So today we are going to talk about the design of a spread or isolated footing, right? Before that, I would like to tell you that what is clear cover. Though you are going to study effective cover, clear cover, resisting moments, lever arm factors, neutral axis in details in design of a structure too, right? However, here I would like to also give you some idea that clear cover is nothing but you can see the slab. The reinforcement is placed at the bottom of the slab. So the outer line of the reinforcement to the outer line of this slab is called as clear cover, right? In case of beam also same, this is the clear cover. Here also you can, in case of column, you can see the clear cover, how the clear cover is there. Here also you can see the clear cover, the outer surface of the reinforcement and the outer surface of the plastered part of the beam. This is called a clear cover. But in case of effective cover, you have to take the from the top, the depth from the top to the center of the reinforcement, right? Now we shall talk about the spread or isolated footing. I'm sorry, actually there was some disturbance in the PPT display. So a spread or isolated are reinforced concrete rectangular footing under a single column. How we can find out the base size? Base size means the area of the footing. The area of the footing, what is the formula? How we can calculate the area of the footing is equal to P plus P dash by small p. What is P? P is the load coming from the structure through the column, right? And P dash is the self weight of the footing divided by safe bearing capacity of the soil. Yesterday also I told you that safe bearing capacity of soil you can calculate by Tarjaki theory or Meyerhof theory, right? And then we can find out the area of the footing. So area means we are going to take the rectangular footing here, right? A spread or isolated reinforced concrete rectangular footing. So L into B, area we can write like this way. This equation will be like this. So here also net upward reaction or net upward pressure, which is also called a net upward pressures, causing bending moment and shear force. How it is causing bending moment and shear force? Can you tell me? Normally, the load is working on the footing in downward directions, but the soil pressure working in the upward direction. That the net bearing pressure, the soil reaction is working in upward directions, which is going to cause the shear failure or the bending moment on the footing. So you can see here, yesterday I also told you that while calculating this net upward reaction, which is PO, we shall not consider the values of P dash. Why? Because the footing area, or we can say the load, the self weight of the footing is uniformly distributed on the soil. So this is not considered, right? The P dash is not considered while calculating the net upward reactions or net upward pressures. So what we shall write? P by A, A is nothing but L into B. Now we shall see the diagrams. This is the section of the isolated footing, right? See, here the length is there, width is there. Bending moment, in this case we are going to calculate the bending moment along the y-axis as also along the x-axis. So this is the plan, right? How the net bearing pressure acting in upward direction. The diagram is also there, PU you can see, and this is bending moment diagram. The D is there. So A and B, C, D, four diagrams are there. So we can discuss about this diagram B. How we can determine determination of depth. How we can determine the size we have discussed in the previous slides. How determination of depth means the thickness of the footing. How we can find out? Because thickness is an important parameters which is going to take the load of the structure. Thickness is also, the area is also important. Area of the footing is also important, and thickness of the footing is also important. These two things are, these two things we have to design, right? Because the whole load of the structure depends upon the thickness of the footing as well as the area of the footing. So you can see here how we can determine the thickness of this footing from bending moment consideration. In the previous lectures also, study lectures also, we discussed how we can determine the depth by bending moment consideration and shear force consideration. So bending moment consideration, what we have to do here, we have to take the bending moment along the y axis. We have to also take the bending moment along the x axis. Along both the axes, we have to calculate the bending moment. And based on the bending moment, we have to also find out the thickness. Thickness is denoted by a small t, right? So as you know, the bending moment m1 we are going to take, because first we are going to take the bending moment along the y axis. So moment is what? Force into area, distance. So force, we can stress into area is nothing but is the force. So force into distance. Then the m1, how is the rho PO is nothing but the stress net bearing pressure diagram, or net pressure, net bearing, net upward reactions also we can say. So this the stress, and this is the area. Area is nothing but the L. L you can see. This is the L. This is the L. So along the y axis we are going to take the moment. So L is the, this total length is total, this length is the L, and B minus B by 2. B total width is B, and B small b the width of the column, right? So this we are going to subtract. So B minus B, capital B minus a small b divided by 2 will be this distance, right? So this the L into this, L into this is the area, the stress into area in distance. So this is acting at the half of this B minus B by 2. Half of the B minus B by 2 is equal to what? B minus B by 4. So if you calculate the moment M1, this will come like this way. PO by 8 into L into this. So this is also wrong here, you can see. This also you have to write. This value will come here, the maximum bending moment, right? So yesterday also I told you D is nothing but thickness of the footing, or depth of the footing also it is called as. So M1 by RB into L. RB is the resisting bending moment. Resisting moment L is the length. So resisting moment, the formula is 1 by 2 sigma CBC JB KB permissible compressive stress in concrete into lever arm factor, neutral axis factors. So what is lever arm? What is neutral axis? Yesterday lectures I told you. So similarly, we have to also calculate the bending moment along the x-axis directions, right? X-axis sections, y-y sections we have calculated. So you can see here the M2, the bending moment along the x-axis is equal to stress into area. What is the area? This is this dimension of this column A into B, a small a into B. So a small a, L minus A by 2. L minus A by 2. That means this length, this width will be there, L minus A by 2 into a stress into B. B because this length is also there. So this B into this length, that means stress into L minus A divided by 2 into B. This will be the area into stress will be the force, and L minus A by 4. L minus A. L, this is the total L minus A by 2 is this distance, and but it is acting at L minus A by 2, half of the L minus A by 2. That means it will be equal to L minus A by 4. Right? So M2 also we shall calculate, and similarly D also we can find out M2 by RB, the resisting bending moment, right? So M2 is called as calculated bending moment, and RB is called a resisting bending moment, right? So in the study slides what we saw, that resisting bending moment should be greater than the calculated bending moment, then the design will remain safe. So effective depth values, because M1 also we have calculated, M2 also we have calculated. So larger the two value we have to consider as the thickness of the footing based on the bending moment considerations. Now we shall go for shear force consideration. Right? Here also shear force we shall calculate in both the direction, along the y-y axis, along the x-x axis. So along the y-y axis, shear force, as you know, stress into area. What is stress? We are taking a stress PO, net bearing pressure diagram. This is the value of PO. So area means a length. You can see here, we are going to take the V1 along the y-y axis, along the y-y axis. So along the y-y axis means, so the L is this is the total length, this is the total length, into B minus B by 2. B minus B by 2 means what? This is the capital B, and this is the small b. The dimension of the column is also there, dimension of the footing is also there. So B minus B by 2, that means from here to here, and minus D, right? So this area, this portion is going to create this shear forces. So shear force is equal to stress into area. What I am trying to say, that how we can know the value of a small d. See, this small d we have to assume first based on the previous bending moment. There also we have calculated d. That d also we can use here, and this d at this distance d, this shear force we have to calculate. So d, the thickness of the split footing, as I told you, at this value of d, shear force has to be found out. Here also we have to find out shear force at this point, right, along the y-y axis. So shear stress Tv1 per unit length can be calculated by this formula. The shear force by area is equal to nothing but shear stress, right? Tv1 V1 along the y-y axis shear force along the y-axis, L into D. So this area, this is the L, this part is L, and this area is D, right? The width is D. So L into D is with area. This part of the this part is going to experience the shear stress, right? The shear force causing along the y-axis. So TV1 we have to also find out. Similarly, along the x-axis also we have to find out V2, the stress into area along the x-axis B. This part is the B, L minus A. This is the L. This is the A. This is the dimension of the column. L minus A by 2 and minus D. Here also, here D actually it is not shown, but this distance is D. Here this distance is D. So this value we can calculate shear force stress into area, and TV, that means shear stress, we can calculate by V2 by V into D. So what we can say here, the TV1 and TV2, this is the calculated shear stress, and what it says that to control the shear force, permissible shear stress in concrete tau C should be greater or equal to developed shear stress tau V1 and tau V2. So tau V1 and tau V2 we have calculated, but whatever the concrete you are going to provide, that should have shear stress more than or equal to the developed shear stress which you have calculated, right? So what it says now, accordingly we have to do the mixed design. Mixed design also we will study in design of the structure 2, M10, M15, M20, M25. These are the mixed design. So based on the mixed designs, shear stress values are also available for the concrete in IS code. So by equating tau V and tau C will be given in the IS code, and tau V based on the mixed design, tau C is given in the IS code, and tau V you have to calculate. Both you have to equate. Then you have to find out the values of small t, right? And here also you can see that larger of the two values we have to adopt as a thickness of the footing. So finally, greatest value of effective depth obtained from bending moment and shear force is taken for evaluation of total design depth D. What does it mean? You have seen that we have calculated M1, M2 based on that thickness of the footing, that is small d, we have calculated there. The greatest of M1 and M2, the values of greatest values of d we have considered in case of M1 and M2. Similarly, we have also considered the greatest values of d in case of tau V1 and tau V2, right? So the greatest value considered from the bending moment as well as from the shear force, right? We have to consider uh, as a small d finally, and the total design depth is equal to effective depth, the small d which you have calculated, plus half of the diameter of the reinforcement plus clear cover of the footing, right? So